Boom. Hello and welcome back to Calculus 1. We're talking about related rates. So, finally, application section full of word problems and situations where we can show off our knowledge. The concept is fairly simple, which is you differentiate an equation to find related rates, and then you plug numbers in. And usually no one has issue with that. But many have issue with setting up the problem because there is lots of geometry, there's a lot of critical thinking and other things that you might not be used to. So first of all, I would like to explain the concept of related rates and what types of problems and things we are talking about. And then we are going to transition into, spicier examples and more useful stuff. We start by examining, let's say, a cube. And say that this is an ice cube. And you leave this ice cube outside in nice 100-degree weather, and you wait a little bit. The ice cube will start melting, and as the ice cube is melting, it is losing its volume. It will shrink and eventually disappear. So the object, in this case, is becoming smaller and smaller and smaller. Volume gets smaller, surface area gets smaller, length of the side of each side edge is getting smaller. So all of these values are getting smaller as the ice cube diminishes in the 100-degree weather. If I'm to call a side A, I can write volume equation as A cubed because it's a cube, so all three sides, edges that we consider in X and Y and Z direction are all A. So we multiply all of them to get the volume. So this is the equation for volume of the cube. Now what happens is we say the change in volume happens in time, which means that if I want to find related rates, I will take derivative in respect to time. So if you are carefully observing now, none of the variables match, and you are not going to encounter the situation as dx dx. So now, as you are taking the derivative, you should always ask yourself first, in the equation at hand, are all letters variables? Because if they are, they get differentiated. If they are not, they get copied over because they are constants. So you have to be careful about that throughout the section. You are looking at this equation and you say volume is definitely changing because the cube is getting smaller as it melts. So therefore volume is a variable. Also on the other side of the equal sign, you see A, which is the length of the edge, which is also getting smaller as the ice cube is melting. So A is also variable because it's changing, it's diminishing, right? So both of the letters that we have there are variables. And I have to treat them as variables as I take the derivative. So when I take the derivative of a v, I get 1, and then times dv dt. So all I have is dv dt. And on the other side, when I take the derivative, I have good old 3a squared followed by dA dt. Remember how we, in implicit differentiation yesterday, we always wrote dx over dx or dy over dx, depending on what derivative we took. So now you have to still keep writing that, except in this case, pretty much all the time they will stay around. Now, this equation here is the mathematical model we are after. This equation is your related rates. And the reason why this is related rates is because there are two rates. You can see two rates, a rate of change of volume and a rate of change of length of the edge. So there are two rates of change, and they are related with the equation in between. So the title tells you what's happening here easily. Related rates means you have to have at least two different rates which are related with whatever equation is connecting those rates. So this problem is technically solved. You can measure, and I had students from math club 4 or 5 years ago go to chemistry lab, and you take the ice cube, you leave it on the scale, set up the water runoff into one of those graduated cylinders, and you wait for the whole thing to melt. You time how long it takes for this ice cube to just melt completely and turn into water. Now, as you time this, you actually measure the rate of change of volume, because water leaving the ice cube, right? You can see how the volume is filling up in the graduated cylinder. So that means that the volume is leaving, so that's your dV dt because it's happening in time. And then you can measure the size of the ice cube. You can do, all other cool things. So the purpose of this introductory example, I didn't give you any numbers, but you will get the numbers and just plug numbers and you find whatever it's missing. That part is extremely easy. This is the hard part of understanding what the hell is going on and how to actually set up the problem. Once you reach this point where you have an equation, from this point on, you just plug numbers in. That's all it is. Now, I talked already about being careful which letters are variables and which letters are constants. I'm going to give you now an example of a problem where one of the letters works out to be a constant. So say you have a can of soda, right? You go and you say, can I have a Coke? And they say, is Pepsi okay? No, it's not. Yeah, why are you laughing? You're one of the...
Those people, and they're like, I'll take Pepsi. And I'm like, no, we have Coke. And they're like, well, I guess they'll be okay.
Yeah.
Like, I'm sorry, I just ruined your night because we have Coke.
So...
One lady yelled at me, like she was really pissed with the Pepsi. I was like, I'm sorry, like I just work here.
That's exactly what you're supposed to provide. Service. Okay, back on track. We have a can of soda. Here it is, live, right? Can. It's a cylinder. It has a radius, R. It has a height, h. The volume of this would be the area of the base, which is clearly r squared pi, because it's a circle on the bottom if you look at the can, right? Times the height. So now you have some kind of liquid inside this can. whatever it is. And as you are drinking this, say with a straw, the level of the liquid will be going down. So it is clear that the volume of the liquid is changing because the amount of volume, right, the amount of liquid inside is the volume of the can. And as you drink the liquid, there will be less and less volume. So we definitely see that the volume is variable because it will be changing. Then we move on to R. Is the radius of can changing as you are drinking the? No, right? Radius of the can would always be, let's say, inch and a half, right? Say inch and a half. So R in this particular problem is not changing. R is constant, therefore not a variable. And then we see the height clearly is a variable because you have, as you drink, you have less and less and less height. So V is a variable, age is a variable, and in this case, R is not a variable, R is a constant. So R is constant. Now, because R is constant, when you take your derivative, you get to copy that R because it's just a constant, just as pi is. So if I rewrite this one more time, R squared pi h, and I hit this with the derivative in time, because, guys, the entire section is the derivative in time. Change happens over time. You grow over time, right? Because once you were born, you were what, 7 pounds? And now some of us are 700, right? So we have change that happens in time. When we take this derivative, dv dt is equal to, and I'm going to copy r squared pi because that's all constant, and I have age, which becomes dh dt, right? Because the derivative of age is 1, followed by the chain rule dh dt. And this would be your model. I will contrast this a little bit later in a class with the similar formula for the cone, and if you observe at the cone, you see that radius changes, right? So if I have a conical can, let's say, filled with liquid inside, you see that the height is changing because the height is the level of water or liquid, whatever is inside, is going down, as well as radius is changing and volume is changing. So in that case, you'll have some product rule to crank, right? So, but we are going to do a whole problem with that, so I don't want to bother you right now. I just want to make sure that you are understanding that it is your job to check every letter that you have in your equation, whether that letter is a variable or a constant, because the way you apply the derivative will be different, right, and dependent on which one is which. The next part is silly question prevention portion of the class, which is, do I have to know all the formulas from geometry for volume and so on? And the answer is, it's Calc1. So obviously you need to know something that you learned in 8th grade or 7th or 6th. But I will help you grind through these volume formulas in 3 categories so you never run into an issue, I don't know what it is, hence I couldn't do the problem. So here is the ultimate, divine summary of all volumes out there. We have shapes that are like this. We call them prism-like. Objects that look like this. All of these objects have the base B and the height h. And the volume for such objects is B times h, where this B is area of the base. Then we have what I like to call spiky objects, which is going to be a cone or a pyramid of some sort, whether it's three-sided or four-sided. It's important to have a spike on the top. Those guys still have the base and the height. Their volume is always 1/3 base times the height. No exceptions to the rule. So you can see now that the cylinder and the cone are both circular, right? They have the same base, they have the same height, but the cone is 1/3 of the volume of the cylinder. You do the same for three-sided, four-sided, or whatever sided pyramid as well. So as long as you are able to find the area of the base, you should be multiplying that by height, h, and then you figure out whether it's spiky or non-spiky object, meaning you put 1/3 or nothing there. The last category contains only one object, and that one object in the last category is sphere, a ball. It's the only in its category, and the volume for this you are memorizing as 4/3 pi r cubed, where r is obviously radius. So this table over here contains everything you need to know for volumes. And now you look around and you say, we are in this room in a box. So area of the floor times the height of the wall, right, from floor to ceiling, is going to be the volume. Very important calculation, because these air conditioning units are the size of the air conditioning unit that will push the air is calculated through the amount of volume that you have to cool off. Put too small, it won't work well. Put too much, it won't work well. A lot of people make the mistake, they own a house and then the air conditioning unit outside dies and they say, oh, it was so and so, I'm gonna get the double one. And then they wonder why they have mold. Well, when you put too much, the ducts are going to condense water and it's going to create mold. And you don't go inspecting ducts on the outside because they're in walls. So important calculation, right? If you are an HVAC person or someone who's designing these systems, is to figure out the volume of each room. And then, so this is how you make money, right? That's your job, to figure these things. So to find the volume of this room, you will just take the area of the floor and multiply it by the height, and that is contained in the first box. If you wanted to find the volume of this hole, well, you can think of this part on the top here as, so this spray bottle, right? This spray bottle, and this spray bottle contains a cylinder whose formula for volume is in the first part, and then you have something that looks like a cone, which is spiky object, whose volume is over there in the second rubric. So you will add the two and you will have the volume of the entire shape. sphere gets its own category because sphere is the perfect object. And sphere has the property that derivative of volume in respect to radius gets you the surface area equation. Which brings us to surface area, another geometry part that you will heavily need in this section. And that is the surface area of the object. As you can see, this object here, this can of disinfecting wipes, has a label on it which has safety information and then the logo and everything else. That had to be designed. Well, it's the surface area, right, where it's what it's glued to. So when you make designs, you have to know what the surface area is, and you send that to marketing department or whatever, and then they come up with a nice graphics design for the label. But they have to have dimensions on how big is the sticker on which they need to come up with the design. Now that comes from you as a designer of the can or the container. You need to know what is the area of this. Now if you are to cut this down the line and unfold, you get a rectangle. Because if you are to put it together, you get a cylinder. So now, what is the area of this rectangle? It is clearly the circumference of the circle on the bottom times the height of the object. Because, holy nightmare, how perfectly this works. Look at that. So, if you look at this paper perfectly, for some reason, covers this object. And as you unwrap, you see how the length of the bottom of the rectangle is going to be the circumference of the circle, which is 2 pi r, times the height of the can, gives you the surface area of the object. And then you have plus this if you need the entire thing, or just need this part. Now, obviously, we didn't need these ones because there's no design there. So for surface area, you still have to, do some work and worry about some calculations and so on. Good. As I said, this is going to be the game of which quantities are getting smaller, which quantities are getting larger in time, and then writing the equations, taking derivatives, so that we can relate the rates. Every derivative is a rate because it is change in time. So I'm losing volume, in my case, I'm gaining volume in time because I eat a lot. But then you have also, and then with that, my surface area also, right, which is the cost of maintenance, like soap, right, and everything else. So you see how one thing leads to another. Larger clothing, for instance. Now, the wording and notation. When the problem says change of volume in time, you immediately know it's dV dt, because the letter D means change, so change of volume in time. Change of some kind of length in time. That could be, let's say, dx dt or dy dt or some of those. Change of area, surface area, in time is going to be dA dt. So we have a lot of these words. They all have the word change in front of them. That immediately means it's related rates. But then they don't even have to say this. They can just say that something is changing at the rate and they give you units. If you are good with units, chemistry and physics are a joke. Joke. Just need to show up for exams if you understand how units work. If someone tells to me that rate of change is 3 meters cubed per hour, I immediately know they're talking about what? Volume in time, so dV dt. Immediately, because meter cube is a volume. Why is it volume? Because length times length times length is volume, 3D. And each length was meters, so meter times meter times meter is meter cubed. So it's volume. Rate of change of something is, let's see, rate of change is -2 feet squared per hour. What is that? Change in surface area in time. So you should be able to pick out this type of the wording and immediately know which quantity is given. Because once you grind through equations and derivative and have everything ready to go, if you're not able to pick information from the text and plug in appropriate spot, well, the problem is going to be wrong. So make sure that you are learning these words that trigger notation and tell you what's what. I had another good example of something, now it escaped me. Oh yes, and one of the most important things, they might ask, how fast is something changing? That wording means, so how fast is, I don't know, blank changing. You see, when you say how fast, that means, again, in time. How fast? How fast happens in time? Are you fast? You're slow, medium, right? So how fast is area changing in time? That is immediately translated as dA dt equals to question mark. How is the area changing in time? So that is immediately dA dt equals to question mark. They're asking how fast is the area changing. So you see that they say area changing, that triggers the derivative of area. They say how fast means dt in time, change in time from, I don't know, it was changing from a minute ago till now. So there you go. So all of these are basic skills that we need to be able to set these problems up and then eventually solve problems. So one more time, we start from the idea that as one concept, one quality of a certain object is changing, the other qualities might change as well. If you have at least two of these changing simultaneously, you are able to write an equation that links them as related rates. So now in purple over there, you see that the change in volume in time is related to change in length of the edge in time using this 3a squared as a link, right? So that's our way to relate these two rates that are given. One of the problems for your project, which will be due the day of the final exam, is asking you simply to work out mathematics of a coffee maker. That's all it says, the entire problem. So what are you supposed to do? You are supposed to measure in time using your cell phone as a stopwatch, or maybe you have a stopwatch, or you're going to do the Mississippi thing. You will run the coffee with the coffee and the coffee filter, just the water without coffee and a coffee filter, just the filter, no coffee, and you will find the different rates. You will find the rate at which the water is leaving, the rate at which the coffee is pouring into the pot, the rate at which the height of the pot in which coffee is getting into, how fast is that rising. Now, some of you will have the filter to be a cone, some of you will have a filter to be a cylinder, some of you will have the pot as a cylinder, some of you will have the pot as a sphere almost. So you all have different types of, and then if you do not own the coffee maker, well, this is not the time for you to buy one because you clearly don't need it. Bunch up with someone, right, who has the coffee maker. And students who take my classes for a long time, starting, let's say, in either algebra or pre-calc, they kind of work as a unit, and they bunch together and work on problems all the time. Learning communities are extremely important for success. If you are trying to, defeat this beast alone, it's a tough battle, and I commend you for that. But still, it's much easier if you have friends and study buddies, to, like, look at me. I have no friends for the gym or anything. This is why I look like this, right? So, but if I had, right, I look better than him. So, anyway. So, what we do is, for this project, if you don't have the coffee maker, because it will be one of the problems, and this is all relevant, you can bunch together and then, measure these things and so on. In the project, you will explain the experiment you did, and you will write the equations that are relevant, and you will, the whole thing will look like, 2 pages of typed text with few pictures that you took of your measurements and the coffee maker and stuff, and occasional number for, thing, an occasional equation. That's how the project looks like. It's applied problems that show you how the money is made with this stuff. It's nothing to do with, it's not going to look like lab, where you have to write all the steps and nonsense that no one cares about. All right, so now let's do some problems, because we can. I'm going to steal problems from homework, from textbook. You do have problems also in the text of which are solved examples. You guys can, work those out, and you can read. So I will work, let's say, on problem number 6, and then you can try problems number 5 and 7. They're all the same with, different geometry, but same wording and everything. So here's problem number 6. It says a shrinking square. The side of a square decreases in length at the rate of 1 meter per second. So the side of a square decreases 1 meter per second. They want me to find the change in area So find the change of area, and B, at what rate are the lengths of the diagonals of the square changing? At what rate the lengths of the diagonals are changing. So we have 2 questions. Now, first question clearly asks about what? So how do I write that mathematically? dA dt. So the entire question is translated into world of math language by writing dA dt, because they are looking for change in area, and that happens over time. Awesome. So let's solve part A. We know everything. We are given the rate of change of a side. So let's say S in time is decreasing, so I will put -1 because it's decreasing. So given ds dt equals to -1, and I put negative again because it's decreasing. So now find the change in area. We are looking for dA dt. And now just a little bit of common sense. They're talking about a square. They're talking about the area. So what equation do I have to differentiate in order for all this to work? What would be the equation that it's connecting the concepts mentioned in the problem so far? S squared. A equals S squared. So it's just an equation for area. So now when I differentiate that, I will get a related rates. So I'm going to differentiate in respect to time and say that the change in area in time is equal to 2S ds dt. Now, one part that I missed while I was reading is they tell us that for part A, they also tell us, so also given that S is equal to 5 meters. They also give us that in the text. So let me read the whole problem now. The sides of a square decrease in length at a rate of 1 meter per second. At what rate is the area of the square changing when the sides are 5 meters long? Five meters long. That means that S is equal to 5 meters. dA dt is the thing that we're looking for. And we have that the ds dt is -1. I get to plug everything in. dA dt is what I'm looking for, so leave that alone. Equals to 2 times 5 times -1. All of these values are there. So it's -10 meters squared per second. How do I know it's meters squared per second? It's area. Meter squared is seconds, right? And then it's divided by the time, which is, in this case, seconds. You can have it by minute, by hour, by month. That's all units of time. Except this problem was in seconds, so. Good. Does this make any sense of what we're doing? Now, part B. Part B is asking about diagonals. Well, if you are having an issue with formulas and things, you can draw the square with the sides S and S, and then try to figure out, let's use capital D for the diagonal. So now, dare I say, it should be clear that diagonal squared is equal to S squared plus S squared, using basic Pythagorean theorem. from where d squared is equal to 2s squared and then from there we can just take square root of both sides, get d equals s root 2. Now it should be plus minus, but lengths are never negative, so we can just ignore it. So I found an equation which connects the length of the diagonal to the length of the side. So link between sides and diagonals. So that is our equation that we are going to differentiate in respect to time. And we are going to get change in diagonal, length of diagonal over time is equal to, and now we take derivative here. Well, it's just root 2, that's a constant, times 1 times ds dt. So now this equation here is your related rates equation. What do? Plug the numbers in. You know that they're saying at what rate is the diagonal changing, so you know that they're asking you how much is dd dt. On the other side, you know that it's -1, right? So it's root 2 times -1 equals to negative root 2, and that would be the meters per second, because the length for, right? It's the length divided by time. You can see length divided by time here, and then this has to match it, because the unit of distance is meters and the units of time is seconds. Now this could be feet per hour, could be, you know. Good. Awesome, right? What you can do is you can put the little snowball on top of the hill and flick it off, and it's going to become this ginormous thing by the time it's all the way down, right? You can calculate at what rate is that increasing. You can do whatever with these things. The next thing that I want to talk, I mean, the whole class is just this, just, you know, different problem. They did a good job in asking the oil spill question. That's your first example in the book. So you have the oil rig which started leaking oil, and then oil spreads. It spreads in a circular manner. How fast is the area changing as you are going? Because the sooner you clean it, the less you have to clean, right? So how fast is how fast is the area changing? You have the equation of the area of the circle, you differentiate it, plug numbers in, you're done, right? It sounds so simple when I say it, because I've been doing this for about 70 plus years. When you're new to this, it sounds cool when in class, and you go home and you just pull all your hair out. Slow down. Pick up the keywords. They're talking about the side. They're talking about area. Common sense. There is only one formula, that is area of that shape, and it will include the side. They're talking about the volume and the side. Again, common sense. There is a formula, which is the link between the volume and the side. So whatever you write, you will eventually differentiate, get those related rates, and then from that point on, you just plug the values in. So let's see a few of these examples. When you see a triangle, triangle will have few different formulas. You have Pythagorean theorem for the right triangle. You have the area for the triangle. You have the perimeter of the triangle. You have the, I said Pythagorean theorem. And then you have all the trig for triangle that gives you the lengths of the sides and the angles. When you see a triangle, it's going to be one of those 10 equations which I mentioned, not all 10. So you pick the appropriate concept and you use it. So let's see, 2 or 3 word problems that will actually have this situation. So here is Mother Earth, and here is a house with a roof, right? I'll put the window so you know it's a house. And here's the gutter, right? You need that for the rain. And that will eventually drain into the foundation of a house. Now, what happens is you get the leaves, and leaves clog everything, and then the rain just creates this waterfall in front of the house. So you want to keep that gutter free from leaves. So what we have here now is the ladder, and the guy on the ladder. With a hard hat, obviously, it's a worker, cleaning the gutter. Now, his so-called good friend sets up the camera and then casually walks to the ladder and then goes, right, with a swift foot movement, kicks the ladder away from the house. Now, since the ladder has constant length, what's going to happen with the top point? It's going to go down, right? The hope is that the guy will be holding, right, with the gutter and then eventually actually rip everything off. So what are we doing here? Well, we have a math problem, right? I clearly have a distance x from the house. I have the height y at which this guy is. And as we kick out this, we create the change in x direction, which is clearly the derivative of x in time, because it's the change of distance in time as you kick out the bottom point for the ladder. Now, let's say the ladder is, 15 feet tall ladder, but it's at the angle, right? And then you have the y, and as the bottom point, the contact of the ladder with the ground, is moving away from the house, then this one has to go down. And again, dy dt should be the common sense there, because it's going to be, again, velocity, unfortunately, going down in this case. Did I mention the camera for YouTube? Yeah, I did, right? All right, good. So now, what you have is, you know how fast you kicked the ladder out, because the camera caught the whole thing. You can put just the grid and use either a Mississippi or a cell phone and figure out how fast dx dt is moving, because you're the one who kicked it. Now, and I hope you guys can all see the triangle here. I mean, do we all see the triangle? And it's a right triangle, for that matter. So what are all of the possible triangle equations that we get to use? One of them is perimeter. One of them is area. One of them is Pythagorean theorem. We have 6 trigonometric functions, right, that we can set up. And you're looking into this and say, well, which one? I don't have any angles, nor I need to get any angles. Therefore, all of the trig is out. So you just killed more than half of them, just by saying no angles necessary. Then you are left with perimeter, area, and Pythagorean theorem. Would perimeter make sense? Would area of the triangle make sense? No, right? Would Pythagorean theorem make sense? Yeah, Pythagorean theorem does make sense. Because as soon as you write x squared plus y squared, equals to 13 squared, which is the ladder. 15, that's what I said. You are not paying attention, please. 15 squared. We can differentiate this and get the dx dt dy dt, right? So what we get is 2x dx dt plus 2y dy dt equals to 0. There's your related rates formula. I'm already done. Related rates, you have the two rates, which are the two speeds. One is the speed at which you kick out the letter, and the other one is the other side of the letter. How fast does it fall? So now, if you see, you can cancel the 2's because they would factor out and divide into 0, so that they're gone. And the only thing for you to do is to now plug all the values you know and go for it. So let's say that you kick the letter out. Well, let's say first x is equal to 6 meters. Say that the letter was 6 meters away from the house. And you also will need how fast you kick the bottom out, so dx dt. And let's say that one is given as, I don't know, 30 meters per hour. All I need to do is to plug all of these values in my equation. So I know that x is 6. And then dx dt is 30. And then you have plus, so that's 6 times 30 plus y. We have to compute y. You see that? We have that x is equal to 6. We have that the hypotenuse is 15. So now you compute the y because you need to plug in y into the equation, and you don't have it yet. So a little side calculation over here will say 6 squared plus y squared is equal to 15 squared, 225. So we get that the y squared is, that's a 36, right? So what we have? Yeah, 189, right? Yeah. And then you will take a square root of 189. Give me the two decimal places. 13.7. What's the digit after 4? So it's 75? Okay. So now you know that this is 13.7, so you will have 13.75 dy dt equals to 0. You see how dy dt is the only unknown variable here. And all you need to do is to now go 180 divided by 13.7. You are going to get about 180. And I'm sorry, not 180. You're going to get about 30 something. So this is equal to 180 plus 13.75 dy dt. So how much is dy dt? $13.01? 180 divided by 13.75?
I got 13.09.
13.09, whatever, okay.
Yeah,
13.1 is fine. Say meters per second. So that's the speed of the guy on the ladder going down if you kick the bottom. What did we use in this problem? We used the Pythagorean theorem. We eliminated other formulas. We eliminated trig because there were no angles. You eliminated all of these areas and perimeters and so on because that was nowhere mentioned. And you have this. Yes?
Did it make a difference since the length of the ladder was you put in feet, but
Oh, yeah.
I was just thinking maybe that's why it was.
Yeah, that's yeah, I should change all of this to feet. Sorry. European. That's how you bury the Mars lander. Do calculation in feet, program the thing in meters, and just crash it.
But that's more accurate, right? No less.
What?
Meters.
Meters are much more, yes. Meters are accurate, yes. And much more organized. I mean, I was born in meters. Yeah, for eyeing things, right? Like, yeah, it's about, right? It's good. Like, yeah, it is. Good, nice. Now, the textbook has a problem similar to this, except what they're doing is they're flying two airplanes and they say, oh, we hope these guys miss each other. Right? Because that's would that be hard actually to manage two planes to miss each other? Like, do we have to do these kind of calculations? Or the air control is just near an airport? You think it's busy, right? Like, how busy is it? Is it busy? Oh, they get paid a lot. I wonder why.
I mean, I'm sure they have algorithms set up. There's no way they've got people just like crunching numbers with like that many people flying around in the air. It's no shot. I told you, it was international.
Want to untangle this one?
That's a lot bigger than they are in real life, too, right?
Yeah, probably multiply that by yeah.
Yeah, they're there. Flying about.
They're racing across the ocean.
Yeah. I'm not sure if Europe is Europe busy at all. This website is so slow. Huh. There we go, finally. Look at that. You're gonna untangle all of this. So it's not done by these calculations, but you said algorithms. What is an algorithm?
Well, I was just gonna like say that it's gotta just be a system of coding.
And who writes that?
Probably software engineers or some
Aha. Well, definitely. Hopefully them, right?
Yeah.
You're not gonna get plumber to write it, right?
No, they get like the bag check and got it. It's like, hey, make like an extra couple $100.
Yeah, sure.
Come throw some stuff together.
So
Pull that.
you have to understand that all of this starts with, let's figure out with the two airplanes, which what it did right now, and then it goes and has more and more and more and more. So you keep adding to the, as you would say, algorithm, right? The software runs all of this, not humans. And then if some glitches happen or issues happen, then the humans try to clear it up quickly, and then, right? So you don't get to be stuck on the airport for more than 2 months. All right, so you have the idea of that particular side of the. Now there's the United States. Yeah, I know this website. You can just stay all day, and actually this is all updated real time. So you can pick any of these airplanes, and then it tells you all of the statistics on it. Gives you the path and then the arrival time. So it takes some time to get all of the info. There you go. Oh, is this thing working still? I know. Each one of them too. All right, so you can enjoy this at some other time. What I want to do is I want to see if we can find a rocket launch. So we can do another problem in engineering. You know, so SpaceX is launching all the rockets, right? And sometimes they have a good shot of the rocket launch. Sometimes they have some, you know, Joe standing on the side with like cell phone, right, recording the whole thing, right? So you can actually design a system that will always have the rocket in the middle of the shot. So as we go to think about this problem, we first draw the whole situation to see, you know, what are the things that we need. So say this is the Mother Earth, and you put the rocket there. And then you're going to shoot the rocket straight up, right, from the launch pad. You are going to set up the camera. And the camera will have this view angle, right, of the rocket. Now, as the rocket goes up, right, meaning the height goes up, you want the center of the camera shooting the center of the rocket. You want the camera to rotate to still shoot the center of the rocket as the rocket is going up. Now you have to design and program, right, a system which will, on the hinge here where the camera is located, which is going to rotate the camera using this angular velocity omega, because that spin on the camera is going to, right, you have the camera looking at the rocket, and then it's going to go and rise and rise and rise. Now, you have to understand that when the camera is the closest to the rocket, both are on the ground, rocket will start off very quickly, so the angle of the camera has to start moving very, very fast and then slow down as the rocket is further up, because the rocket is actually accelerating, but because it's further away, it looks like that it's slowing down. Actually, we will need to adjust the camera angle less as the rocket goes further. So now you would have to program that. And the way you program that is you come up with mathematical equation, you plug that into the computer. The computer will be sending the signals to the motor, which will move the camera. Now this is something that you can actually build because it's very simple. Now it beats me why no one ever built such a device for the actual cameras that shoot these launches. So say that the camera is, I don't know, how many feet away? What is a good distance? 60? Oh no.
Like further away.
No, we are talking, no, not miles. How about anywhere from like 500 to 1,000? Let's pick a number, it doesn't matter. 500 to 1,000. 750. You like it. All right. So we'll make you happy and we'll put 750. There we go. So that's the fixed distance. I don't want to call that distance D because you set the camera on a fixed distance and the rocket is going to go straight up. So that distance is fixed. What's changing is clearly the height, which will be changing the rest. Now, I hope you understand that we are chasing the angle over here, angle theta. So we start with our equations and, do we all see the triangle first? We all see the right triangle there because I'm going to erase it. Cool. So what do we have? We have age, we have 750, and we have angle theta. What concept should relate to these? Area of the triangle? No. Tangent, nice. Trigonometric function tangent solves our issues because you have the opposite, adjacent, and the angle. Tangent, for those of you who forgot your class that you just finished 2 months ago, tangent is given as opposite over adjacent. So now, looking at this problem, tangent theta is equal to opposite is age divided by 750, which is the adjacent. Well, I already have the equation, now I just need to take the derivative of it in respect to time to let these things move. What's the derivative of tangent theta? Secant squared theta times d theta dt, right? Change of angle in time, guys, that's your omega. Angular velocity. And all of this is equal to the derivative of age is just going to be 1 over 750 dh dt. And what's this dh dt? Yeah, but what is it in the real life with quotation, because we have a fake life here now? It's not the rocket position. Yeah, but what is it? What is it measuring? Yeah, but what is it? What is it at? Thank you, speed of the rocket. Speed of the rocket up. That's all it is. See how simple this stuff is? It's amazingly simple. And you see how just the things that you need that play the role are in these equations. You write one equation, you take the derivative of it, and boom, you have all you need. So what do? Now I can solve this for d theta dt, because d theta dt, which is omega, is equal to, you move secant to the other side, so you will have 1 over 750 dh dt times 1 over secant squared theta. But what secant squared, 1 over secant squared is? Cosine squared. Nice. So we get that omega is equal to cosine squared theta over 750 times dh dt. There's your equation. The rocket, the speed of the rocket is known. You get those updates all the time. So you can plug that in the equation. You start your theta at 0. And as the angle theta rises, it tells you how fast the camera has to turn. So as you can see, it's very simple to create such devices. This is how engineering works. You have an idea, you develop it on paper, and then once everything looks okay, you create a prototype, you tweak it, you mess with it, you make it better, and then eventually start doing the production. So that's the process. From idea through calculation, through prototype to the product. Again, if you need to go further in this, I would ask you for the angle at 30 degrees where the speed of the rocket is so and so. You will plug those two numbers in and you will give the omega. What are the units of omega? Anyone? Radians per second, right? It's angular speed. So it has to be the unit for measuring angles, which is either degrees or radians, but we measure in radians, because you always say radian per second. So if you ever took the physics course now, this probably is much clearer than if you do it without calculus. Here, memorize this formula, and then, right? It's much clearer if you do it this way. So try to complete this problem. A spherical balloon is inflated at a rate of 0.5 feet cubed per minute. What is the rate of change of its radius when the radius is 10 inches? What is the change? What is the change of radius when radius is 10 feet? Just realized it. Oh, I read from two different problems. This 0.5 should be 15, and that's it. Oh, you're using pens? I know. Which geometrical shape are we talking about? What concepts of a sphere we are talking about? Volume. You already have the volume equation. somewhere in your notes. If it's not in your head, it should be in your head by today, 7:30 p.m. And just differentiate, plug in, you're done. And go get some air out of there. So this one is understood as one of the basic problems because it's just a single equation. You just plug everything in and you are done. We start with the volume, 4/3 pi r cubed, which we differentiate in respect to time to find the rates of change. So change in volume over change in time is equal to 4 pi over 3 and then 3r squared dr dt. Both volume and r are variables, so they get differentiated. Now these 3's cancel, and we have dv dt is equal to 4 pi r squared dr dt. Now we have that r is equal to 10, and dv dt is 15. So we are going to plug those values in. We have 15 is equal to 4 times pi times 10 squared dr dt. Observe that they are asking us at what rate is the radius changing, the length of the radius. That's exactly what we have there as a variable. So dr dt is equal to 15 divided by 400 pi. That's feet per minute, I think. Was that minute? Yeah. Feet per minute. You can divide by 5. So dr dt, which is the change of radius, the length of the radius in time, is 3 over 80 pi if you divide by 5. Feet per minute. And that's the answer. I left the spicy problem last. All previous examples, in my humble opinion, are basic examples because you have a single equation which you differentiate, you plug in numbers, you walk away. This example will be spicier. And then if you really want to challenge yourself, there are some very interesting, insane examples in a textbook like number 19. The number 29 will be very relevant to your project, let's say. And then you have anything in 30s. Sorry, not number 9, for project number 46. And then you have these really interesting problems that are later on. Having the most insane problem, problem 52. If you want to call yourself boss of this section, figure that one out. I have a solution. It took some time. So if you're interested, we can talk about it. The last problem I want to discuss in the last 7 minutes of the course, so please pay attention, we'll have to kind of rush a little bit, is a conveyor belt is bringing sand in, which drips onto a pile. And clearly that pile is going to start as a cone, which is going to grow in time, and grow in time, and grow in time. So we are going to have, because we know how much sand is coming in, we have the inflow of volume, which is dv dt, the amount of sand that it's coming in time. So you will know that you will have 3 cubic feet of sand coming in within a minute, or whatever the unit is. You want to design a system that will shut off this unit because you don't want this sand to go all the way, pile up at the conveyor belt and eventually break it. So we need to find an equation which will relate the volume with the size of the cone, which is the obviously height and the radius. Now, as I mentioned before, when you have a cone and you look at from the side, you have the height h and the radius r, and both of them are changing. As the height grows, in this case, the radius is going to get smaller, right? So first, we start by noting that we need the volume equation for the cone. Volume equation of the cone, it's a spiky object, is 1/3 area of the base, which is pi r squared, times the height of the cone, which is h. And then we say, okay, I need to figure out the related rates equation. So you immediately differentiate this, but this is where you have to be careful, because now you have three variables. You have the change in volume, change in radius, and change in height, which means that the right-hand side has a product rule. Yeah. So derivative of v is 1 times dv dt equal to, and now you have a pi over 3, which is a constant, times, and here is your product rule, in between r squared and h. So copy the first one times derivative of the second, plus copy the second times derivative of the first. So we have to do the product rule, and we have to remember that every time when we take the derivative, we follow with the chain rule. Remember from the implicit section, dx, dx, dy, dx, where right now is going to be everything dt, so dh dt and dr dt, where we took the derivatives. And now you can say, okay, dv dt is equal to pi over 3, and now what I have is r squared dh dt plus 2h r dr dt. This is your related rates equation, stage 1, because we can do better. So you see that we have the change on radius and the change in height. But that is, well, too many rates there. So we can eliminate one of them. We can eliminate one of those because if you look at the geometry of the cone, if this is, let's say, 5 and this is 10, the smaller values would be h and r, and you can set up the proportion. So I picked any numbers, 5 and 10, but the problem will give you what the proportions are for the, I think one of these is in homework anyway. So now you can set up the proportion and say h is to 10 what r is to 5. Which says that h is equal to 2r. All right, when you cross multiply, you get 5h equals 10r, and then you divide by 5 and you get h is 2r. So once you have this, h is 2r, you can differentiate that in respect to time and eliminate some of the calculations above. So as you can see, now we're getting dH dt is equal to 2 dr dt. So what is the dV dt now? When I plug this in, it's pi over 3, open parenthesis. We are going to let's keep every h and eliminate all r's, because or you can eliminate r's and keep h's, whatever. Less. So which one do you want to keep, r or h? Doesn't matter. Pick one. You want to keep h? Okay. If you want to keep h, that means r's have to go. So we're going to solve this for r, which is 1/2 h, and we're going to solve this for dr dt, which is again 1/2 dH dt. So now we plug everything in. R squared, that's going to be 1/4 h squared. Leave dH dt alone. Plus 2 times h, leave that alone. R needs to be 1/2 h. And dr dt is given as 1/2 dH dt. That's a lot of calculations there, but it's worth it at the end. I have 1/4 h squared dH dt, plus these guys drop, and I have 1/2 h squared dH dt. Observe that both of these are h squared dH dt. We can actually add these, just deal with the fractions in front. So this is dV dt is equal to pi over 3. 1/4 and 2/4 is 3/4 h squared dH dt. 3's die. And look how simple this equation turned out to be. Pi h squared dH dt. Now that is a much better version than the one we had up there. So now I know how much the volume is changing, how much sand is coming in. I can measure the height using my eyes, because there might be behind the sand pile marks of how tall the pile is. And I can calculate how fast it's changing. It is pi over 4. Yeah, right there. You see it? It says pi over 4. Again, you are given numbers like in previous problems. You plug those numbers in, and so this is a spicier example because we used the similar triangles there, and found a way to simplify this problem. And that takes care of the 310. So let me just say bye to the stream first. Bye, stream.